two cars started traveling towards each other from two locations a distance d apart, along side-by-side, straight parallel roads with uniform speeds of 45 miles per hour and 30 miles per hour respectively. After 2 hours, the distance between the cars grew by 30 miles over the distance between them after 1 hour. The value of d in miles, and that's what we have to determine, and we are given 5 choices and we have to pick the right answer. So this is a time distance problem that's pretty universal across different high school tests and standardized tests like GRE, GMAT, SAT, etc. And what helps solving such problems sometimes, and especially in this particular problem, is a pictorial representation. So we have two cars that are traveling towards each other, and they are initially separated by a distance of d. And let's suppose the red car is traveling with the speed of u, and in time t, as the cars are approaching towards each other, the red car will travel a distance of ut. And let's assume that the blue car has a speed of v, and in the same time it will travel a distance vt. So here the assumption is that the cars have started simultaneously towards each other. So after a time t, and here after means a time t after their start, which I've assumed that's simultaneous. So a time t after their start, and assuming that this is before they cross each other, the distance between the cars would be basically d minus ut minus vt. This is very, very clear from this particular figure, right? So that's why it helps to have this pictorial representation of the problem. So remember, this is before, so we are assuming the cars haven't yet crossed each other. So that's how their separation or the distance between them will look after a time of t. So as they approach each other, we can write the distance between them, x is equal to d minus ut minus vt, and if we take t common, we are left with d minus, within parenthesis, u plus v, and that multiplied by t. Now this makes sense from just a generic perspective. So what this equation tells us is, in unit time, so if t is equal to 1, the distances between the cars will reduce at the rate of u plus v. So u plus v is basically their relative speed. And since they're traveling, in opposite directions, the relative speed will basically be the sum of their speeds, sum of their individual speeds. And what is u plus v? Well, that's given as 75, because u is 45 and v is 30, so u plus v, the relative speed is 75, right? So at some point, the cars will cross each other, and let the time of crossing be denoted by capital T. So how do you find at what time the cars cross each other? Well, at that particular time, the distance between the cars will be 0, because they're crossing each other, right? So in that orange equation, if I substitute x equal to 0, and if I substitute small t by capital T, which is, my time of crossing, and let's represent that point of crossing by this green dotted line on the figure. We have basically d minus u plus v multiplied by capital T is equal to 0, because x is 0, right? So we just substituted x as 0 in that orange equation and substituted small t by capital T. I'm just denoting capital T as a time of crossing. And from this, it's simple to see that the time of crossing capital T will be essentially d divided by u plus v. So that's the time point of crossing. Now, the question is, what happens once the cars cross? how does the distance between them change? Because as they approach each other, we know the distance between them was reducing, right? Because they're approaching each other, and that rate of reduction in unit time was simply the sum of their speeds, which is u plus v 75. Now, after the time of crossing, that blue car will now in time t. So here I have basically put t minus t because I'm just measuring the time since crossing. So capital T is the time of crossing, and small t is still the time I'm measuring with respect to the starting time. So that was the original time when the car started. But here I'm just interested in the distance the cars have traveled since the cross. So that's why within parentheses for the time I have small t minus capital T. So the blue car traveling with the velocity or speed of v will have traveled a distance of v multiplied by small t minus capital T. And similarly, the red car would have traversed a distance of u multiplied by small t minus capital T. And so the separation between them would be basically x is equal to v multiplied by small t minus capital T plus u multiplied by small t minus capital T. So this is also very, very apparent from the figure itself. And this can be written as, you take small t minus capital T as common, and you're left with u plus v multiplied by small t minus capital T. So after the time point of crossing, in unit time, the distance between the cars will grow at the rate of u plus v, and u plus v is 75. So why? And this is pretty evident from the equation itself, because so what I'm saying is after, in unit time after time of crossing. So if I set in the purple equation, if I set small t minus capital T as 1, then I have x is equal to u plus v. So that's the rate at which the distance between the cars will grow since their time point of crossing, or after the time point of crossing. So that's also equal to u plus v, and we know u plus v is 75. So what we have so far is before crossing time t, the distance between the cars reduce at the rate of u plus v, shrink at the rate of u plus v. And after crossing time t, the distance between them grow at the rate of u plus v, because now they're still moving in opposite directions, but instead of moving towards each other, they're kind of moving away from each other, right? So that's why the distance grows. Now, according to the problem, between hour 1 after the start and hour 2, and we are measuring the time from their start time, the distance actually grew by 30 miles, right? So compared to the distance after 1 hour, the distance after 2 hours was more than the distance after 1 hour by 30 miles, which is kind of surprising, because if both of these time points were before the cars crossed, then in 1 hour, I would have expected the distance to shrink by 75 miles per hour. If both of these time points, 1 hour after start and 2 hour after start, if those happen to be after the cars crossed, then I would have expected the distance to grow by 75 miles in 1 hour, right? But the fact that it grew only by 30 miles tells me that these two time points, so 1 hour and 2 hours, must be on either side of the crossing time, meaning that t equal to 1 hour must be before the cars crossed, and t equal to 2 hours must be after the crossing time. So that's why from the time point of t equal to 1 hour to t equal to 2 hours, so in this 1 hour time period, the distance between the cars actually reduced first as they still continued to approach each other, and then at some time point in between 1 hour and 2 hours, they actually crossed each other, and from there on, the distance started increasing. So the distance between them in this 1 hour period from t equal to 1 hour to t equal to 2 hour didn't grow all the way by 75 miles. It grew only by 30 miles because during some portion of this time, their distance reduced as they were approaching each other, and they crossed at some time point between these two times, and thereafter the distance between them again started increasing. So this is the conclusion that we can make. Now we can find out what the distance between them was after 1 hour, because we know that 1 hour was before their crossing time. So we basically go back to that orange equation, x is equal to d minus u plus v multiplied by t. We substitute x1 for x1 meaning the distance after 1 hour, and for t we substitute 1. So we have d minus u plus v multiplied by 1, and we know u plus v is 75, so we can write x1 is equal to d minus 75. We still don't know what d is, right? That's something that we're trying to find out. So what was the distance between them after 2 hours? Well, we know 2 hours must be after crossing, right? So now for finding the distance between the cars after crossing, we refer to the purple equation, right? The equation purple, which is x is equal to u plus v multiplied by small t minus capital T. And in that equation we substitute x2 for x, because we are just trying to denote the distance between the cars after 2 hours by x2. And for small t we substitute 2, because we know small t is the time measured with respect to the starting time. So it's 2 hours after the time of start, right? And we have capital T, but we already know what capital T is. So capital T is basically d divided by u plus v. So we substitute that, and then we take the parenthesis out, we do some simplification, and we get 2 multiplied by u plus v minus t, and u plus v is 75, so this becomes 150 minus t. So we have the time after 2 hours, or rather the distance x2 after 2 hours is 150 minus d, and the distance after 1 hour was x1 is equal to d minus 75. So these two are important results, right? And we just clean some space up here, and we carry over these important results. And according to the problem, it's given that x2 exceeds x1 by 30 miles per hour, right? So that's an easy way of rephrasing the problem, so that we can actually set up an equation like this. x2 is equal to x1 plus 30, and then x2 is 150 minus d, x1 is d minus 75. And when we write that out, we have a simple linear equation in one variable, and it's very easy to solve for d. So d comes to 195 divided by 2, and then when we convert it to decimal, we have basically 97.5. So the correct choice for this question would be the option D, 97.5.